For our project, we're designing a set of frames for reading glasses that can allow the wearer to adjust the magnification as needed. Now, this is done by a dial on the frame that will move a second, smaller lens left and right across the main lens. As you can see in the picture, this dial here moves the second lens back and forth, changing it. The change in the second lens positions alters the focal point. Now, the two set of lenses will be added by the optometrist after the lenses are made to the proper prescription. This way, they can custom tailor to the individual while still allowing for flexibility with the focus adjustment. Now, you may ask, why do we want to create this? Those of us in our group who wear glasses, like myself, know how it could be hard sometimes to have a prescription that works for all circumstances. Sometimes it is harder to see either close up or further away, depending on what the prescription is sent for. We find ourselves taking the glasses on and off or tilting our heads to look over or under them. Now we are attempting to improve this issue by manufacturing a set of eyeglass frames that will be adaptable to different circumstances while maintaining the wearer's entire field of view. Now I'm going to talk about the ideal material properties. Frames need to be lightweight so they sit comfortably on the wearer's face without putting pressure on the nose or feeling cumbersome. They should also have medium flexibility. The frame should be able to conform to the wearer's temple and ears while still fitting securely. Ideally, it would be better for the frame to bend rather than break if potentially put under average daily stresses. For this goal, we will look for high values of both yield strength and elongation of failure. We want to consider comfort and durability, which are our primary goals. Some of these material properties are lightweight, comfortable, which is density, plastic technologies for flexibility, yield strength for avoiding plastic deformation, and elongation to failure for avoid breaking. We then consider four materials commonly used in frames. These are titanium, stainless steel, beryllium copper, and cellulose acetate. Although cellulose acetate has the lowest density, we had to rule it out because of the exceptionally low yield strength. We next ruled out stainless steel because it had the lowest elongation to failure percentage. Choosing between beryllium copper and titanium was a harder choice. Titanium is half the density, has a slightly lower elastic modulus, and a slightly higher elongation of failure. Still, beryllium copper has 4.5 times the yield strength of the titanium. So either way, there were going to be compromises. We ended up deciding on beryllium copper, reasoning that a major difference in yield strength made up for slight differences in elongation to failure and elasticity. We did give up the lower density, but we calculated that the end difference of set of frames would be approximately 0.02 pounds. Now we had to decide a supplier for this beryllium copper. Our choices were Materion, Chon Kapai New Material Company, and Belmont Metals. We decided to use Materion for a supplier since they have the lowest price per amount of material we need for one set of frames, including the freight cost. For our end of life considerations, any frames we get back can be disassembled to refurbish and save whenever possible. Beryllium copper can be recycled through the supplier Materion. The material can take anywhere from decades to centuries to decompose on its own. So recycling is the only responsible plan of action if we cannot reuse components ourselves. Now I'm going to leave it to Alexander to talk about the material structure.
In general, beryllium copper is either hot worked by pouring into molds or cold worked by shaping, grinding, or cutting. Its versatility comes from it being highly ductile to begin with, and its large increases in yield strength, durability, and toughness after an age hardening stage. There are two types of heat treatments used in the overall processing: solution annealing and age precipitation. First, the supplier melts pieces of beryllium into molten copper to ensure the beryllium atoms are evenly distributed throughout the copper. The temperature of the mixture is kept no higher than right at the solidus line, and both the temperature and time are tightly controlled throughout the process. This prevents the gain structure from growing too large, which would result in a loss of material strength. At the end of the process, the material is quenched in water. The resulting alloy is highly ductile at this point and is ready to be cold worked into a product. Once beryllium copper has been worked into a product, age hardening is used to strengthen it. This is done by heating the piece to lower temperatures of about 200 to 400 degrees Celsius, followed by long cooling times. The long cooling times of this process allow the beryllium atoms to separate themselves from the solution and form berylides along the grain boundaries, giving the alloy greater strength and hardness. One other advantage of the alloy is that it is resistant to hydrogen absorption. During hot working, such as welding and electroplating, some materials will absorb hydrogen into their composition, which makes them brittle and easily susceptible to fracture under stress. Beryllium copper does not exhibit this behavior. One thing to be careful of when working with beryllium copper is that the alloy should be kept away from chemical compounds such as polyvinyl chloride or vulcanized silicone while they are being cured. The fumes given off can corrode the beryllium copper. Beryllium copper is only toxic if inhaled in the form of dust, mist, or fume. Inhaling beryllium can cause chronic beryllium disease, which is a lung condition that blocks the exchange of oxygen. Next, we have our process selection. We had a few options for processing metals. We ruled out forging, hot rolling, and cold rolling first. Since we are making eyeglass frames, we need a process that would be more suitable for smaller components. For the rest, we next weighed the pros and cons of each one. Lost wax casting. Lost wax casting involves making a mold of the part that you want out of ceramic. After pouring the metal into the mold and allowing it to cool, the ceramic is chipped away to reveal the new metal object inside. This method is useful at creating objects with intricate geometries and could allow us to make our frames with fewer pieces to have to join together. However, we feel that having to chip away at the ceramic from the thin parts of the frame would involve too many defects to be financially efficient. Die casting. Die casting uses pressurization to force molten metal into a reusable die. This gives the object a smoother finish than lost wax casting and is still able to form objects with complex geometries. This method would involve the extra costs of furnaces to heat beryllium past its melting point of 1,590 degrees Fahrenheit. Since we can already get the metal in the wire form we need, this processing method involves too much cost and liability that we do not need. Next, we have Derek talking about process selection of CNC machining.
CNC machining uses a computer-programmed mill that cuts away at a piece of metal in 3 dimensions until the desired shape is formed. It can also engrave on a surface and drill holes by automatically switching to the proper bit. While the process can produce intricate and complex parts, ours are relatively simple. We could get a few components out of one block, but that would mean the employee would have to constantly swap out old blocks for new ones, bringing down the method's efficiency. On top of that, blocks of beryllium copper would get wasted trying to get it small enough to form eyeglass frames. We would also need additional safety precautions because beryllium can be very toxic if inhaled, not to mention all the tiny particles of metal floating around in the air. The machines cost an average of about $200,000 a piece, which is pretty high for what we're trying to do. We also considered DMLS, or direct metal laser sintering, which is a way of 3D printing metal objects. First, the desired geometry is programmed into a computer. Then the computer lays out a thin layer of powdered metal in the necessary shape. Then a laser fuses the metal particles together. This process is repeated layer by layer until one solid object is created in the shape and form it was intended to. These machines are just as, if not more expensive than the CNC machines, costing about $250,000 apiece. However, there's next to no wasted metal, being that you only use what's needed. Although being fast, the machines carry a pretty high price tag, which deems the process unreasonable. And remember, we can obtain our material in the form we want, eliminating the need to create it from scratch. We also looked into CNC wire forming, which is another computer-controlled process, but instead of milling away at a block, this machine has arms that can bend wire to any angle in any direction as programmed. And after bending the wire, it cuts it to the correct length, and then the process repeats again and again until finished. Because the wire is continuously fed from spools, we can do large batches in little time no matter how complex the part is. These machines are considerably less costly than the other automated systems, averaging between $35,000 and $55,000. We like this process because of its simplicity. It has the least amount of steps needed to make our final product. Along with the minimal startup cost and speediness of production, this is the ideal startup process. As demand for our product grows, we can easily add more machines, with each one dedicated to a specific component of the frames, greatly increasing production. Another process considered is brazing, which is like soldering, only at a higher temperature, and this process results in a much stronger bond than soldering. For brazing, the filler metal used to join the bases must have a melting point above 840 degrees Fahrenheit, but below the solidus of the bases. For beryllium copper, an aluminum silicon alloy is commonly used. It has a liquidus of between 1,185 degrees and 1,659 degrees Fahrenheit, thus falling in the range needed to form an incredibly strong bond for our components. When brazing, the base metal is heated to the proper temperature, then the filler metal is placed in contact with the base, melting the filler and joining the bases as it cools. We would need to load the components into the brazing machine, but the automation would not only increase the speed of production, but increase the level of safety for our employees too, which is well worth the higher cost of the machine in our opinion. After a lot of thinking, we decided to go with a two-phase process for our glasses. We'll start by shaping the frame's components. Beryllium copper comes in a wire form, so we won't need to remold the material. The wires fed into the CNC wire bending machine, and that forms the shape of the frame. This allows us to program the style into the machine and create entire batches all at one time. The frames will need to be formed in 7 sections. The front of the frames will be 2 pieces, as if you cut them vertically right down the middle. And these are what hold the lenses in place. Each piece will also have an arm attached for a nose pad, and on either side will be the arms that extend back over the ear. After all the pieces are made, we'll start joining them together. The ear rest arms will be joined to the main section with a screw on a hinge, allowing them to be folded when you're not using them. Another screw will clamp the frame fronts around the lens once it's installed. The nose pad arms will be brazed to the main section, while the actual pad is held into place with a screw, so they can be replaced if need be. Once the frames are assembled, the adjustable lens mount will be brazed to the main section. Now Tyler's going to talk about what kind of time we're looking at and a few final thoughts.
Thanks, Derek. So I'm going to go into some of the numbers that we came up with as far as machine time. As well, we're going to look at some of the safety concerns that we've looked at during this process, as well as some manufacturing difficulties that we're anticipating through the process. Lucky for us, the components of our frames has a very simple geometry, so it limits the complications that we can have. To kind of demonstrate the process of bending our frames through the CNC machine, I have queued up a quick video just to demonstrate what the process looks like here. As you can see it's a very quick process, and there is lower chance for things to go wrong. The wire bending machine can form 5 of the components that we have within our glasses at the rate of 1 bend per second. 2 pieces that hold the lenses have 3 bends, so they can be formed at a rate of 1 every 3 seconds. You can see here in the chart, we have illustrated some of the times that we've come up with per batch of glasses here. At these rates, all of the components for a batch of 100 complete frames would take 1,100 seconds, or approximately 20 minutes. For our estimations, we will round the figure up to 1/2 hour to allow time for changing of the programming and changing of the components as well. The brazing process should take around 4 seconds per joint, and then pieces is moved down the assembly line for the next piece to be brazed to the frame. There are 6 braze points that we have to take into consideration when looking at the times here of the frames. So we have a rate of 24 seconds to complete the frame of our glasses. Another thing we looked at is our safety concerns. For the CNC bending portion, there's no environmental concerns that we have to worry about. There's no fumes or extreme temperatures, so that area is of less concern. But we are working with automated machines, so protecting employees from physical danger is important. We have to worry about body parts getting caught in machines, anything like that. So that is something that we considered, and some of the solutions we've come up with is guards and barriers around some of our automative machining. Brazing would require a little bit more safety concerns on the other hand. Face eye shields must be worn to protect from any sparking. Heat protection must be worn because with high temperatures involved with bonding the materials, we want to make sure employees are safe. We also, with high temperature and these materials that we're using, we want to make sure that we have proper ventilation. So that's something that we've considered as well as far as our safety concerns. Some possible difficulties that we've looked at during the manufacturing process. We've taken a look at some of the most likely. A few that we have come up with is wire breaks in the machine, software bugs, any kind of software issues that has to pertain to our machining, our CNC machines, and then actual physical repairs to our machines. The solutions that we've come up with as far as wires breaking in our machines, the wire snapping or breaking could be quite dangerous if it is started getting whipped around from the machine. For this, any other potential dangerous situation, we would have emergency protocol in place and taught to all of our employees. So in the case of an emergency or something not going right, we would make sure that our employees are trained for the situation if it came up. Software bugs or any kind of software issues with our machining. Most companies that sell CNC wire forming machines offer tech support. So we would rely on that, anything beyond the scope of what our employees could handle. So we would offer, some basic entry-level training so that all of our employees would be able to understand our software. But anything beyond that, we would reach out to the manufacturer of the machining. And the same goes for physical repairs for the machining. Taking care of physical components of the machining would be in two parts. We would want a few staff members trained in machining as well as with the software and repairing the machinery. We would have schedules in place for regular preventions of the machines, prevention maintenance. If the machining is needing repairs that's beyond what our staff is capable of handling, then again, we would reach out to the manufacturer of the CNC machine. In conclusion, we feel optimistic about the product and our processes. Using beryllium coppered and brazing most of our joints will result in a resilient product that will last a customer for years under normal use. Using the process of CNC wire bending will keep our product time to a minimum without a high overhead of some of the types of machining like CNCs or lasers. Something we would like to research and develop in the future, because with a company like this, you always want to be innovating more, is to push the limitations that we currently have with our focusing. Right now, these types of glasses only work for lower level prescriptions, such as reading glasses. We would like to find a way for these to work with higher levels so that people with more limitation visions could regain some of their sight that they have lost and can live a normal life again. Another consideration could be automated glasses that can detect objects in the wearer's line of sight and auto adjust to the focus. If we could use some of these technologies as a starting point and customize it for our purposes, it could be something groundbreaking for the people living with low vision.